Hi guys, we're going to talk about subgame perfection. So I have two examples. The game one is a game with perfect information, and game two is imperfect information. And the reason is here, as you can see, player two can perfectly observe player one's actions, left or right. But in the second game, player two cannot observe whether player one has played L or R. And so the second player has an information set. Everything else, the payoffs, the name of the actions, everything else is the same. All right, so here, let's analyze these games. So remember, this is an extensive form game, and we said we can find the Nash equilibrium of this game by writing down the normal form representation of it, and then we can find all pure strategy and mixed strategy Nash equilibrium. However, not all Nash equilibrium are satisfying this condition we called sequential rationality, meaning whether players reach to a subgame or not, meaning some parts of the game, well, the players should always choose their actions or strategies optimally. Remember the non-credible threat idea. So instead of finding the Nash equilibrium of this game, let's directly apply the backward induction and find the subgame perfect Nash equilibrium. So the backward induction is very intuitive, very easy. Let's start from the lost player. So here the lost player is clearly player two because no one else moves after the second player. So let's start from here. So if the game comes to this point and player two decides to choose between U and D, she will clearly choose D because remember the second payoffs are the payoff of player two because action D or strategy D is going to give her a higher payoff. Well, however, if this decision node of player two is reached, well then she's going to decide between again U and D, but this time obviously U is going to lead to a different payoffs, right? Because the player one has played differently. And so she's going to look, U brings her 2 payoff, D brings her 0 payoff, and therefore U is the optimal strategy. Well, then we're going to build upon this. So this is going to be sort of our foundation. And then the first player is going to think, well, look, I can choose left or right, all right, at this decision node when I come to this decision node or when the game comes to this decision node. When I choose L, I shouldn't worry about whether my opponent is going to choose U or D because she will observe what I have chosen and she's a rational individual. I know she's going to choose U. Therefore, if I play left, I'm going to get 1 payoff. If I choose right, however, just follow the arrow, I'm going to get 2 payoff, which is better. So you know what? Right is better than left. But I also have another option, right? But for now, do not worry about what you would choose here because I am worrying about or I am considering what player one choose at this particular decision node. So when you find optimal decisions, just go one decision node at a time. So therefore, in this decision node, player one has 2 strategies, pure strategies available to him, and clearly right is going to bring him higher payoff than left, and so he's going to go for right. And then finally, the very first information set or decision node, which again belongs to player one, and he knows that if he chooses M, he's going to end up, just follow the arrows, he's going to end up payoff 2. If he chooses N, however, he's going to end up payoff 1. So clearly 2 is a better payoff. So he's going to play M rather than N. So you know what? We actually found out the subgame perfect Nash equilibrium outcome. It's very easy. Just follow the arrows. 2, 2 is the subgame perfect Nash equilibrium outcome. All right, this is outcome. I am going to now write the strategy profile, which we will need, trust me. So that means in this game, if players play this game, they should end up 2 and 2 payoff. this is our solution. This is our prediction for this game when we apply the concept of backward induction. Well, the question is, what is the subgame perfect Nash equilibrium strategy which leads to this outcome? Well, simple. Remember, strategy profile is strategy for player 1 and strategy for player 2 because there are only 2 players. Well, for each player's strategy, remember, is a function which maps every information set to an available action. Meaning, for every info set, for every decision node for player 1, I have to put one action name. So how many decision nodes? So here there's no info set, or all the info sets are singleton. And so there are only 2 decision node for player 1. So therefore, for each decision node, one action. Remember, that's what constitutes strategy for player 1. So that means one strategy, not one strategy, the subgame perfect Nash equilibrium strategy. Here, for this decision node, it's M. For this decision node, it's R. So the first player's subgame perfect Nash equilibrium strategy is going to be MR. Not NL or NR. And then for the second player, remember the second player also has 2 decision nodes, this one and this one. So therefore, for each decision node, one action. All right, this is what constitutes strategy for player 2. But what is the subgame perfect Nash equilibrium strategy? Well, at every decision node, you have to write down the action which has arrow on top of, or the sort of the branch that has arrow on it. So here in this decision node, this branch is U, and in this decision node, the action is D, that this is the branch where the arrow is on, and so UD is the subgame perfect Nash equilibrium strategy profile. So this is the strategy profile, SPNE strategy profile. Okay, well, once again, so if players play this strategy profile, player 1's utility out of this strategy profile, MRUD, is going to be equal to utility, or the payoff of player 2's payoff under this strategy profile. They're equal, and they both are equal to 2. All right. Well, how do we find it? Well, very simple. So once they play this strategy profile, that means player 1 is going to play M here. Player 1 then is going to play R here. Very good. And then player 2 is playing U here, but I don't care about this because the game has never came to this point. So this is what matters. And player 2 is going to play D here. And so therefore the final payoff is 2. All right. Again, just follow the arrows. Okay, so this is how we solve this extensive form game by using the backward induction. Well, exactly the same game, just one big difference is that the player 2 this time cannot distinguish these 2 decision nodes. So how are we going to solve this game? Can we still say this is the subgame perfect Nash equilibrium outcome and this is the subgame perfect Nash equilibrium strategy profile? Well, not really. Why not? Well, let me first start with this strategy profile. So, is this strategy profile subgame perfect Nash equilibrium in this game? Well, I don't know. Let's apply the backward induction. Can't I? Well, I can. Very naively, you may think, well, once again, when player 2 is in this decision node, which strategy is he going to pick, U or D? Well, he's going to pick U. So I should put arrow here. All right. And then here, what is he going to pick? Is it U or D? Well, once again, D is giving higher payoff, so it's D. So, well, that's it. I found the optimal strategies for player 2. Now move up. Well, can I really do that? No, you can't. That's very important. Why you can't do this? Well, remember, player 2 cannot distinguish whether he or she is in this decision node on the left or on the right, or in this decision node that's on the left. What does that mean? That means she cannot have a strategy where she plays U sometimes and plays D sometimes. Here she can, because she can say, I am going to play U because I know that player 1 has played left, and so I am in this decision node. But here, she can't say, I am going to play you or I am going to play D, because she can't observe where exactly she's at. So you see what I mean? So she cannot choose two different sort of actions at these two different decision nodes. Remember, the strategy, the definition of strategy for each info set, and here player 2 has only one info set. Here she has two info sets, and both of those info sets are singleton. But here this info set has two decision nodes. And so the strategy, remember the definition, again, we come back to the definition of strategy. If it is not clear, trust me, the rest of the concepts is not going to be clear. So you have to clarify what strategy means in extensive form games. Once again, so strategy means for each decision node an action, all right? While here, player 2 has one decision node, so therefore her strategy should be just one action, like U or D. All right? So therefore, the strategy for player 2 in this game is not going to look like UD, DD, UU. It's just either U or D. All right? So that's a big difference. And so, also, let me also say the following. Remember when we applied this backward induction idea here, we said player 2 is going to play U here because it's optimal and D here because it's optimal. Well, yes, you can do this sort of optimization when player 2 can distinguish these two nodes. But the thing is, when she cannot do that, all right, so she has to consider the following. When I play U, I may end up 2, right? But I may also end up 0, which I don't know, right? Either 2 or 0. That totally depends on what my opponent has played. So therefore, player 2's belief about, so here, there's no belief because you're going to observe it, right? When you see something, I mean, here obviously, like when you see something, you know that it's a fact, right? But here you don't see the action of player 1, and so there is no factual. Here you can just believe some form a belief about what your opponent may play, and so maybe you believe that your opponent is going to play left and right with equal probabilities. All right, so that means player 2's belief is actually very important here. All right, let's put the belief aside for a moment. What I want to say is the following. When player 2 sort of considers what strategy is optimal, again, she cannot say U is optimal because, as you see, U is, yes, better than D when this is the decision node she's at, but U is definitely worse than D, so there's no strict domination between U and D for player 2 when she is at this decision node. So therefore, when she considers or sort of evaluates what the optimal strategy for her in this info set, she's going to consider I may get 2, I may get 0, so therefore I don't know. So I have to form a belief. So you see what I mean? This part of the game is more like a static version of this game. Player 1 chooses left, right. Player 2 chooses U and D. And therefore the payoffs are easy. LU is going to bring 1, 2. LD is going to bring 3, 0. And then RU is going to bring 1, 0. And then RD is going to bring 2, 2. Right? I mean, it's very much similar because in this game and in this game, the optimization, even though I applied the backward induction, remember I said player 2 should think that she may be here or here, and therefore she should consider both payoff 2 and 0 versus payoff 0 and 2. So exactly the same, dynamics here, right? So That means when we use the backward induction here, we didn't really have this sort of 2x2 or 3x3 game. It was just one branch versus the other. So the decision was simple. So meaning the concept of optimal decision was simple. Either one branch or the other branch. It was more like a choice problem. Here, however, it's not really a choice problem. This is just a game, right? That we keep analyzing since the beginning. So what if instead of yes, we can use this idea of backward induction, but here, what is optimal strategy? Well, let's suppose the optimal strategy in this part of the game, later we're going to call it subgame. Let's assume that players are going to play the Nash equilibrium here. All right, and then, so let's find the Nash equilibrium. If player 1 plays left, the optimal strategy for player 2, or the best response, is U. If player 1 plays right, the best response is D. Well, now if player 2 plays U, the best response is both left and right. If player 2 plays D, the best response is 3, right? So therefore, you know what? Here, there's only one Nash equilibrium, which is LU. All right, with the payoff 1, 2. So why don't I, instead of doing this, solving this, why don't I solve the following game? I know my space is limited, but let me use a different color. Hopefully it's going to make things easier. So player 1 chooses M or N. If she chooses N, the payoff is going to be 1, 1. If he chooses 1, they're going to come up to this part of the game. And in this part of the game, we assume that the players are going to play their optimal strategies, by which we mean Nash equilibrium strategies. And there's only one Nash equilibrium here. Again, ignore mixed strategies. Well, it's LU, so that means payoff 1 and 2. All right, so then the question is, what is the optimal strategy for player 1? Well, both N and M, right? Because both of them brings a payoff of 1 to player 1. Now I can create the subgame perfect Nash equilibrium strategy profiles and outcome. And in fact, here, let me summarize it. There are 2 subgame perfect Nash equilibrium outcomes. The first one is payoff 1 and 1, all right? And the other one, the payoffs 1 and 2. Well, if there are 2 outcomes, that means there are 2 subgame perfect Nash equilibrium strategy profiles. So what is the first one? Well, the first one is the following. Player 1, so here, remember, put the arrows if you would like to. And if that is going to make your life easier. And here, how am I going to put the arrows? Remember, in this part of the game, player 2 is playing U, right? So put U both, right? Remember, she doesn't remember, she can't know whether she's here or here, so she chooses U in both. And player 1 is playing left, not right. All right, so therefore, when I write down this subgame perfect Nash equilibrium strategy, once again, so I'm going to write the strategy for player 1. How many info set does he have? 1, 2 info sets. So for each info set, 1 action. But those actions must be the ones that have, or the branches that have the arrows. So therefore, player 1's optimal strategies, subgame perfect Nash equilibrium strategies is ML, all right? And player 2's strategy is U. All right, so this is the first SPNE. The second SPNE is player 1 is playing NL, and then player 2 is playing U, all right? So that's it. Well, we can't have a strategy something like M and L for player 1, or you see what I mean, and U, or MN comma U. So these are not strategies. Why? Because once again, this contradicts with the definition of strategy. Strategy is an action, one action for each decision node. So this is for first decision node. This is for second decision node. But what the heck is this? So here you're putting two actions on one decision node, which is violation of the definition of strategy. All right, so this is not a strategy. Same here. This is the first info set. This is also an action from first info set. They're not from second info set. The second info set actions are left, right. So therefore, this is again a violation of the concepts of strategy. Hence, these are the subgame perfect Nash equilibrium strategy profiles. So now I would like to compare these two games. So the first comparison is the outcomes. So in this game, we see that if subgame perfect Nash equilibrium is our solution concept, 2-2 is going to be the outcome, meaning both players are going to get, we expect them to end up payoff of 2. In this game, however, our solution concepts lead to two potential solutions. It could be 1-1, it could be 1-2. But nevertheless, player 1 is going to get payoff of 1, right, which is less than the payoff he can get here. Player 2, however, may or may not get payoff of 2. So that depends on which equilibrium strategy profile they will end up playing with. Nevertheless, whether they play the first strategy profile or the second, both of them are regret-free, or nobody would actually want to revise those strategies because both of them are sequentially rational. All right. So here, the one question is why, these two games are sort of exactly the same. Just one thing is like the player 2 cannot distinguish these two names, nodes, and this actually hurts player 1. But why is that so? Well, here is why. Remember here, this nice strategy, nice outcome, 2-2, can be reached only if player 1 plays right here. Agree? So question is, why player 1 does not think of playing right here? Well, or put differently, why this, we know that this strategy profile cannot be cannot be used here because player 2's strategies are not like UD, UD. It's either U or D. But you know what? We can translate this strategy profile that's going to fit to this game, right? How so? For example, we can say, all right, if you are player 2 and cannot distinguish between U and D, this decision node and this decision node, why don't you, for example, play this strategy profile, MRU, okay? Or, I don't know, MRD. So here, what matters is not, U here, D here. So what matters is playing D here, right? So therefore, we would like to get payoff of 2. So, if they play U, they're not going to get payoff of 2. So therefore, ignore this. So this MRD, MRD is going to lead to payoff of 2. So question is why this is not subgame perfect Nash equilibrium, or why this is not optimal, why this is not regret-free. Well, let's suppose it is optimal. Question is, are those players play these strategies, or will they prefer to revise it along the way? Well, let's see. I would like to put my arrows now on on branches according to this strategy profile. So therefore, let me just rewrite them. So I said player 1 is going to play M, and then he's going to play R, and then finally player 2 is going to play D. But don't forget, she can't really distinguish between these two decision nodes, so therefore she is just playing D, but player 1 knows that. So if he wants, he can actually, instead of playing right, he can play left and get 3 rather than 2, which is actually what player 1 is going to do, right? So he's going to cheat. You see what I mean? So if this is the strategy, so suppose this is the optimal strategy, everybody agrees that they're going to end up better payoff in this and so on. Well, the question is, are these two smart guys, rational guys who would like to maximize their own payoffs only, will really play this strategy profile? And my answer to this question is no, because player one has actually incentive to deviate here. How so? Well, suppose player one plays M, very good. And then player two can't see anything, but according to this strategy, she should play D. So she's gonna play D, whatever player one does. And then the thing is, she will actually realize that her payoff is not 2 but 0. Why is that? Well, because player 1 is not going to choose right. Because he knows that, or he believes that player 2 is actually going to play D, right? She's going to stick to that strategy, and so she's going to play D. Well, then she should play left and get the re. Well, one sort of common confusion is the following. How does player 1 knows that player 2 is going to stick to her strategy and play D? What if player 2 also deviates? You see what I mean? So maybe player 2 also deviates and play U instead of playing D. So then maybe playing left is not going to be profitable deviation for player 1. You see what I mean? So that's a very good question, very good confusion. But here's one thing, guys. So don't forget this, okay? Nash equilibrium. This is the idea of optimal strategy in our sort of solutions of games. So here, for that reason, when we are checking if something is optimal or not, what we do, as it is the case in the definition of Nash equilibrium, we keep everybody else's strategy fixed, as if they are not going to change those strategies. And then look one person at a time and see if she would or he would love to or like to deviate to somewhere else. Okay, so so it's more like a comparative static analysis. Fix everything else, only change one variable. Well, the thing is, if this is not your solution concept, meaning if everybody else at the same time can deviate, well, obviously a bunch of weird things could happen. But to be honest, this is not an implausible way of checking optimality. And in fact, there is a solution concept which checks deviations through groups. A group of players deviate. All right, it's not just one player at a time, but maybe both players will deviate or may deviate. And so the problem or the question is, will deviation here, so a single person deviation benefits player 1, but what about two-person deviation? Maybe both player 1 and 2 will deviate at the same time. So maybe you also would like to see that two-person deviation should also be beneficial for player 1. If it is not, well, then maybe it is. So you see what I mean? So the concept of optimality is not a God-given fact. It's something we defined. And the underlying principle in our optimality concept in game theory basically comes from the concept of Nash equilibrium, which says fix all the players' strategy and then look at deviation one player at a time. And this is exactly what we do. So here I said player 1 is going to play M. All right, this is not the part he wants to deviate. All right, if he deviates here, he's going to get 1 anyway. So it's no better than 1. So the deviation he is considering is here. But what I do, I assume that everybody else, here there are only 2 players, so that means player 2 is going to stick to her strategy, which is D, and then player 1 has incentive to deviate, and therefore I say this strategy, MR, is not optimal, is not best response. This is what we mean, all right? So the best response to D. And hence, this strategy profile, forget about subgame perfect Nash equilibrium, it is in fact not Nash equilibrium. All right? Okay, so the bottom line is the following. In games like this, where information is perfect, backward induction is very simple because, as I said, the concept of optimality is simple. It's, it this branch or that branch that is optimal, given that the rest of the players' optimal actions or strategies have sort of found. However, when it comes to games like this, where information is not perfect, well, the concept of optimality is a bit more, involved or involving. And so we have to be careful about it. So for that reason, we are going to make the following statement. Remember, previously we said, if you solve a game through backward induction, the strategy profile you're going to get is called Subgame Perfect Nash equilibrium. Well, now, however, we would like to extend this idea, and instead of using backward induction, or we would like to extend the idea of backward induction, and so sort of make more formal definition of Subgame Perfect Nash equilibrium. So this is what we're going to do next.